You are currently the only person in this conference.
Okay, so in the lecture now, my lecture, we have to continue to speak about ferromagnetism, and this requires, of course, that we speak about magnetic interactions, because until now, as you saw in my last lecture, we spoke about classical theories of magnetism. So we did not go yet into details from where's coming the origin of magnetism, especially of ferromagnetism. I'm speaking here, of course. And today we will discuss this, and we will have to go a little bit into quantum physics. So this requires to go into quantum physics. Of course, I will keep on a relatively superficial level on quantum physics. I'm also not an expert on quantum physics, so I will not teach you too much on that. But of course, in order to understand ferromagnetism, we have to at least to write down one Schrödinger equation and so on. But before going into details of this lecture, I already announced last time, I would like to make a summary of what we saw in my last lecture. And I do this usually by asking you a few questions. So please try to respond quickly to them in the chat, or switch on your microphone if you can, and tell me quickly what you think is the answer to these questions. So the first question is, what was considered in 1820 to be the origin of magnetism in materials? Please, otherwise we will sit for 2 hours. You know that. Think about currents, electrical currents. Yeah, it has something to do with Balthazar law, of course. Yeah, it was considered that electrical currents create a magnetic field, and so it was thought that in the magnetic material we may have some very small microscopic ring currents described, and this was the theory of Ampere. What kind of different magnetic materials do exist? So today we will speak about ferromagnetism, but the other types of magnetism that we discussed last time, very simply, write it down quickly. Diamagnetic, paramagnetic, ferromagnetic, ferrimagnetic and anti-ferromagnetic materials. Yes, the last ones we will discuss briefly today. Okay. In fact, antiferromagnetism and ferrimagnetism are just special cases of ferromagnetic materials. What characterizes diamagnetic behavior, and how can it be described classically? Now think about susceptibility. susceptibility of a diamagnetic material. What is it? Okay. Nobody wants to say anything. Monday morning is not the right moment. Susceptibility is negative of a diamagnetic material, and it's constant. And we try to make a derivation of the diamagnetic susceptibility by using simply electromagnetism. This was done, this classical approach was done by Feynman. However, it derives quite well this diamagnetic susceptibility. Let's go on. What characterizes paramagnetic behavior and how can it be described classically? Please, somebody wants to answer. Think again about susceptibility. You know that, of course. I cannot make you write something today. So, of course, here we have susceptibility is positive, but it's not increasing with increasing field as in diamagnetism. It saturates at a certain point, and this depends on the fact that we have pre-existing magnetic moment. We did not discuss from where is coming this pre-existing moment, no? Remember that. We also saw that susceptibility is proportional to 1 over T, and the proportionality constant is the Curie constant. Everything was described by the Langevin theory. And this Langevin theory we also used to describe ferromagnetic behavior, and this was done by Weiss. He simply added this idea that in a ferromagnetic material, since we have a spontaneous alignment of spins, or let's say magnetic moments, again, not considering from where they are coming, we have inside the material an additional field. So not only the applied magnetic field from outside, but we also have the field inside the material, and this is the Weiss molecular field. And this field, of course, Weiss assumed, should be proportional to the magnetization. And again, we had there a kind of Curie law. You saw that because we have a transition from ferro to paramagnetic behavior at a certain temperature, and this is called the Curie temperature. And I would like to show you now what I did not do last time very quickly, and I hope so we will get everything quite awake now. A short experiment of showing you the Curie temperature. Of course, this is kind of obvious experiment, but nevertheless, it's nice to see it. I will share my screen. Okay, let's go. You can see here a strong magnet, neodymium boron, and a material which has a very low Curie temperature. You see here this magnetic material is attracted by the magnet. Heat it up only with the candle. You see that it goes away from the magnet, but still being in the field, of course, of this strong magnet, no? As soon as it cools down the material, it goes back. So it's a reversible process, of course. Okay, so this is just to show you quickly the effect of Curie temperature and the fact that every ferromagnetic material at a certain temperature transits to the paramagnetic phase. So this is important to remember. So I already made a summary of the Weiss molecular field theory, and this was done in 1907. And you saw this picture here, that one moment will align with the field that is given by all the other surrounding magnetic moments inside the material. And we have this proportionality between this field created by the magnetic moments and the magnetization, of course, given by the Weiss molecular field constant lambda. But we also saw, and this was quite strange, that this lambda is very, very high. So while we may have a magnetization in a ferromagnetic material of about 2 Tesla maybe, the molecular field of Weiss is calculated to be about 1000 Tesla inside the material. And this, of course, is strange because inside the material, we have a molecular field of 1000 Tesla, but the magnetization that we actually observe of a material is about 2 Tesla. And so this is not coherent, of course, and shows us clearly that we are dealing with a phenomenological theory that very well describes, however, the behavior of a ferromagnetic material. But in order to find these incongruencies, we have, of course, to apply quantum physics. And this is what was missing at that time in 1907 still. Because quantum physics was still in its childhood at that time. And many things were not yet understood. But now, of course, we understand that the origin of magnetization is coming not from ring currents in a magnetic material, but is mainly coming from an orbital magnetic moment, but also from a spin magnetic moment related to the electron. But at that time, first steps towards quantum physics were coming from spectroscopy. And especially emission spectra were investigated at that time. And maybe if you studied physics, then you also studied this emission spectra of hydrogen. Several series, if you remember, and one of the series is the Balmer series. And Balmer investigated this already in 1885. And he found something very remarkably. He found a law that the frequencies emitted of the light emitted by hydrogen correspond to this, are proportional to this formula here, where n are integer numbers. So since these are integer numbers, at that time it was not understood at all from where it's coming, no? All this pointed a little bit now towards the fact of the beauty in physics, no? The laws were considered at times still that they have to be as simple as possible, as nice as possible, and having frequencies, of course, proportional to a law, which includes only integer numbers, was very it was not understood, however, from where it's coming. Everything was understood much better, you can see, but a long time later, so almost 30 years later, when the atom model was understood better. And this was done mainly by Rutherford and Bohr. And of course, the Bohr atom model now describes also these emission spectral lines, because now we know that the frequencies emitted from an atom are proportional to the energy, to the difference of the energy levels of the different atom orbitals. So electrons in the Bohr atom model can only stay on quantized orbitals, and they are characterized by integer numbers. And a transition, of course, has to be from one orbital to another orbital. And you can see here that the Balmer series would be all transitions to the final state of n equal to 2 quantum number. So another point towards quantum physics, and also with this effect, it was very clear that magnetism was not yet fully understood, and this was the Zeeman effect. Essentially, the Zeeman effect, the classical Zeeman effect, let's say, could be understood still by classical theories, and this was done by Lorentz and Zeeman. And in 1896, and here again, we consider, of course, this orbital or cyclotron motion of the electron around a nucleus. And if we bring this material or this electron in a magnetic field, then we will have an additional effect, and this is the precession motion that we studied in the last lectures. And of course, according to this precession of the magnetic moment given by the orbital motion of the electron around the magnetic field, we may have a lower or a higher frequency of the spectral lines in the Zeeman effect. And this, of course, you can imagine that the frequency of the precession motion may sum up according to the orientation of this orbital moment. So if it's clockwise or counterclockwise, we'll sum up or we'll subtract. And this was calculated by Lorentz on the Zeeman effect. But this is the normal Zeeman effect. So we have the splitting of a spectral line in a magnetic field in two lines. And this is still classical, let's say, but it was not clear at all, considering the anomalous Zeeman effect, how one spectral line could split up in more than just two lines. And this happens in the anomalous Zeeman effect. And we will see later that this, of course, depends on the quantum number, the magnetic quantum number, which usually has not only two states. Let's say the final death for classical theories in magnetism was the Bohr-van Leeuwen theorem. And this was found in 1911 by Bohr and in 1919 independently by this very young student van Leeuwen at the time. And this simply describes in a statistical way that magnetism is not possible in a classical system. So at finite temperature and finite magnetic field, there can be no net magnetization at thermal equilibrium. And this was given a theoretical proof by both of them. And you can see this nice picture here in the book of Blundell. And if you give a look to the chapters that I indicate at the end of the lecture, this is a nice interpretation to understand this theorem. So if you think about your magnetic material having a lot of small ring currents inside the material, then you can consider that at a certain boundary border of your material, as is indicated here, you will have a net current, let's say, considering these small ring currents, that is going in the opposite direction than the small ring currents inside. You can see here, this would be all counterclockwise, while this net current here at the border would be clockwise. And this net current will give a magnetic moment, let's say, that compensates completely these small ring currents inside. So, of course, this is just a picture to understand this idea which is behind this Bohr-van Leeuwen theory. And so at the end, we would always have a net zero magnetization. So magnetism is a quantum phenomenon. It cannot be interpreted classically. And therefore, we have to understand something more about the internal structure of an atom and the two different kinds of magnetic moments that we can have. So the orbital magnetic moment and the spin magnetic moment. The proof for the spin magnetic moment, which now, of course, we know that exists, and in fact, it is, let's say, in many ferromagnetic materials, the main contribution to magnetization. This spin magnetic moment was shown experimentally to exist in the Stern-Gerlach experiment in 1921, very famous experiment where Stern-Gerlach used neutral silver atoms, and it was known that the orbital magnetic moment in silver atoms was zero. And Nevertheless, they found that these silver atoms get deviated in a gradient magnetic field. So some will get deviated up and others will get deviated down. So towards higher fields and towards lower fields. So we have 2l+1 subbeams. And of course, it was understood then that there must be another source of a magnetic moment, because otherwise, without a magnetic moment, we would not have any deviation of these atoms. And Gauss-Schmidt and Uhlenbeck in 1925 gave a theoretical proof of the existence of the spin magnetic moment of the electron. So once we know that the source of magnetic moments in your material are spins and orbital magnetic moments, then, of course, we should understand how these magnetic moments sum up. And I always want to make this example because most of you, of course, studied physics and studied a little bit also of quantum physics, but many do not remember exactly how orbitals fill up with electrons in order to give a net magnetic moment at the end. And therefore, I do this example usually. So asking what is the magnetic moment of an iron ion. So I take this example of an iron ion because we have iron localized, let's say, in an oxide. And I take the example of a typical hard magnetic material, barium ferrite, where we have the iron ions take a 3+ oxidation state. So, and now I would like to fill up all orbitals with you with electrons. And if you want to help me, of course, this would be very nice. And of course, we have to know the atomic number of iron, which is 26. And so we have 23 electrons to fill in the orbitals. So first of all, let's remember the quantum numbers. Of course, the principal quantum number n, which is describing the shell, has numbers from 1 to infinite, all integer numbers. Then we have L, the subshell. We have M, which is describing the orbital, the magnetic quantum number. And then we have S, the spin quantum number. Okay, so L, the subshell, can take values up to n-1, and usually we describe them with letters. So S would be 0, P 1, D 2, and so on. Then we have M, the orbitals. And the orbitals can take up to 2l + 1 values. Usually they go from L, L-1, and so on to the negative values. And then we have, of course, the spin quantum number, which can take 2 states, spin up and spin down. Okay, yes. Now, in order to fill in orbitals with electrons, we have to know the Hund's rules. The Hund's rules, of course, describe laws in quantum physics. And they summarize these laws in a quite simple way. I don't know if somebody of you remembers the Hund's rules. If you want, you can write down one Hund's rule if somebody of you has an idea. Okay, I will tell you because it's not so easy, of course, to remember them because it's something like that you have to know by heart. Okay, first of all, Hund's rules say that you have to maximize S. This is the first Hund's rule, and the order is important. The second is to maximize L, and then the third tells you how to combine L and S to the quantum number J. So if you're in a less than half-filled orbital, then you have to combine them by L minus S. Otherwise, you have to combine them to L plus S. Okay, now let's try to fill in our electrons. So we have 23 electrons to fill in our state. So we start, of course, with the lowest energy quantum number n equal to 1. Then we have subshell S equal to 0. We have, of course, then M equal to 1. And we can fill in 2 electrons in this S orbital. So spin up and spin down. Let's go to the second shell. Here, of course, we will have again an S subshell and a P subshell 1. For the S subshell, of course, everything stays the same as before. For the P, now we can have 3 orbitals, 3 different orbitals, because we are in 3-dimensional space. And the p orbitals, if you remember, the p orbitals have a shape like 3-dimensional 8 or infinite sign, let's say, and it can orient in the space, of course, in 3 dimensions. So in the S again, we have 2 electrons to fill in. In the P, since we have 3 different possibilities, we can fill in 6 electrons. Now let's go to the third shell. And here we have subshells, of course, again, S, P, and now we have D. D is the unfilled shell, let's say, in the magnetic elements like iron, cobalt, and nickel. And it is responsible for magnetism since it's unfilled. And that's also why we call these elements, very often you will see 3D elements. Okay, for S and P orbit subshells, everything is the same as before. And now we add the D subshell. So in the D subshell, we have 5 different possibilities. The D orbitals are quite complex, let's say. They are not as simple as the P orbital, which is this 3-dimensional 8. They are more complex and they can take 5 different orientations in space. Okay, I already filled in all electrons up to the 3p state. Now there's missing this 3d state. Now let's count simply the electrons that we have here. So 23 electrons. We had to fill in. Let's see how many we have. 2, 4, 6, 10 here. 10 plus 8, we have 18 already filled in. So 23 minus 18, there are 5 electrons missing. And now I ask you, applying the Hund's rules, how do I have to fill in these 5 missing electrons in these orbitals? If you can, please switch on your microphone and say it or write it in the chat. One electron per orbital, yes. Pointing in which with the same spin. Yeah, perfect. So this is the final solution. So if I apply Hund's rules, I would start now with filling in one electron where in the high S state. So it could be -2 or +2, for example. So here, for simplicity, I put it in -2. The next electron, of course, I cannot put in the same orbital because otherwise I would minimize S, and I would also minimize, let's say, L, because it would be, I know it would be, if I put, sorry, I would minimize S. If I put the electron in the 2 state, for example, here, I would also minimize L. So I have to put it again in the on the negative side, -1. Then the next electron, if I have 3 electrons, I would put here in the 0 state. In this way, again, I maximize L, I maximize S. And then I go on. I have to, at the end, I have to consider the first Hund's rule. So maximizing S is more important than maximizing L. Here I'm still in the less than half-filled orbital. Exactly, I'm half-filled orbital. So at the end, we have S is equal to 5 because we sum up all S numbers, and L is equal to 0 at this point. So what we have in this 3+ ion of iron, we have 5 elementary Bohr magnetons. So 5 mu Bohr magnetic moment of one single ion. If, for example, the oxidation state would be different, let's take a 2+ oxidation state, which is not the case here in this oxide, in this ferrite, but in other ferrites you find also this 2+ state. So then I have to fill in another electron, and I have to fill it in, of course, in one of the highest L orbitals. So you have here that 2 spins are compensated at the end, and we will have 4 mu as a magnetic moment, so S is 4, but L at the end is 2. So here we have also a contribution of L. So in this case, we don't have any contribution of L, of the orbital magnetic moment, only spin contribution. Here we have also a contribution of L. I just want to mention, it's not, let's say, that important, but keep it in mind that very often, however, L in the 3D, let's say in magnetic materials with 3D elements is 0. It's this is called quenching of the orbital momentum. Although for the single ion, you may have a contribution, as it is the case here, because this is a single ion, not in a crystal, let's say, not this calculation that we did. But if you have a crystal, then you have also a crystal field, and this is the electric field that is caused by all surrounding atoms of this ion. So it's not independent, this ion. And since it is not independent, you can imagine that the orbitals are not that free to orient as they would do in a single independent ion. And since the electrons then are influenced by this electric field around, very often the orbital momentum is 0. So they are not free to move, let's say, in a very simplified reasoning. Okay. So we have 2 sources of magnetic moments, spin and orbit. Of course, you can imagine, since both of them are magnetic moment, also they interact, somehow. How do they interact? we can make a very simple classical interpretation of this. If you take a nucleus here and an electron on a cyclotron motion around it, then of course we have this magnetic moment L given by the cyclotron motion, and we have the magnetic moment S of the single electron. Of course, this situation is completely equal to a situation where we have the electron fixed and the nucleus spinning around. And this now we can calculate classically. So we give a classical interpretation to this interaction between orbital magnetic moment, spin magnetic moment, very often also called spin-orbit coupling. So how to do that? Let's calculate by using Biot-Savart the field of a current loop. Now we have a positive current loop, the current loop of our nucleus that is spinning around the electron. Okay, you can do this calculation very easily of this magnetic field. And now our magnetic moment, of course, is coming only from the spin, from this electron spin here. And you can calculate Zeeman energy in this way. And you find here, of course, the derivative of the Coulomb potential. And this is proportional to Z. And this is describing already the spin-orbit coupling energy. So this energy is equal to the spin-orbit coupling energy. And you can see here that the Coulomb potential is very important. So the stronger is bigger is the nucleus, higher is the atomic number Z, the stronger is this Coulomb potential, and the stronger will be also this derivative of the Coulomb potential. And this is why we have spin-orbit coupling very strong, usually in heavy metals, for example, in heavy materials. So what does it mean? It means simply that our spin magnetic moment will align with the orbital magnetic moment. It will somehow feel the field of this orbital magnetic moment. And that's why it calls spin-orbit coupling, because they couple to each other. Very often you will find it written in this way, spin-orbit coupling energy. So not considering here anymore that we have this Coulomb potential, but you write simply the potential, and you write L and S as operators we do in quantum physics. This is just coming from a transformation, as I show you here, from the other formula that I showed you before. So the question is, of course, why I am telling you all this, why LS coupling is so important. Of course, you can imagine that there's some interaction, but why is it important? And this is due to the fact because in this way, the spin somehow couples to the lattice, and there are several effects that influence more, let's say, the orbital motion of the electron. But due to the fact that the spin is coupled to this orbital motion somehow, and the spin may have a bigger contribution to magnetism, magnetism somehow is coupled to the lattice. And one of the effects that influenced a lot by spin-orbit coupling is magnetocrystalline anisotropy. So this is the effect that magnetization very often wants to point in a certain direction with respect to the crystal directions. Of course, related to this again are magnetoelastic effects, and we will have a full lecture where this is part of the lecture at the end of the lectures given by Vittoria. And you may also have non-collinear effects. So now we always spoke about that the magnetic moment wants to align, of course, with all the other magnetic moments, as was considered by Weiss, for example. But this is not the only possibility. Sometimes there might be, let's say, higher order exchange interactions or anisotropic exchange interactions that prefer a not perfect and not alignment, let's say, so that one spin will align at 90 degrees, preferably with respect to the other spin. And now these non-collinear effects were studied a lot. For example, one of the famous names is the Chaloshinsky-Moria interaction, if you're a little bit into spintronics. And then, of course, there are many effects like spin-dependent scattering and transport, and also they depend on spin orbit. So think about the so-called spin Hall effect, which is one of the major effects that are used in spintronics in order to reveal spin currents, the existence of spin currents. So you see there's a variety of effects that really depend enormously on spin orbit coupling, although spin orbit is considered something like a higher order effect. Okay, now I'm at the end of the first part of the lecture. If you have some questions, please ask them now. Otherwise, I will switch my slides. If you, of course, you need to have a break, then please tell me. Otherwise, I continue. I upload the second part of this lecture. Okay, if there are no comments and no questions, I go on. And now we really have to go into exchange interaction, because I mentioned this term now already several times. Now, as we saw that, of course, the spin will interact with the orbital momentum, but of course also spins have to interact with each other, and orbital momentums have to interact with each other. So this origin of this interaction we did not yet discuss, and we have still to understand this in order to say something about the origin of ferromagnetism. So let's go into this exchange interaction, and let's consider a direct exchange interaction. So the interaction between two neighboring localized spins. So localized at an atom, let's say. And this will describe ferromagnetism, antiferromagnetism, ferrimagnetism. And everything started in 1928 with Heisenberg. And he understood this kind of Heisenberg Hamiltonian, which we write now very often in magnetism, and we use this as the main source of magnetism. And it's given by this J times S in S. And J would be the exchange constant. And you can see, of course, this Heisenberg Hamiltonian becomes an energy minimum if J is positive. So in this case, we consider only collinear spin configurations. So if the spins are parallel, then J has to be positive. If the spins are antiparallel, then J have to be negative in order to have an energy minimum configuration. And this antiparallel would be antiferromagnetic state. So the ferromagnetic and the antiferromagnetic state have origin in the same phenomenon. So still in exchange interaction, now only considering that the exchange constant can have different signs. Now I show you here this famous Bethe-Slater curve. And you can see here the interatomic distance divided by the subshell radius as x-axis. And on the y-axis, we have the exchange interaction, or exchange integral, it's very often called. And you can see here different kind of elements and crystals, let's say. you have iron-iron in the BCC configuration, nickel-nickel in the FCC, then and so on. And or manganese, these 3D elements, of course. You can see that the exchange interaction can vary from negative to positive to a maximum, and then it goes to 0 with the interatomic distance subshell radius. And now the question is, why do we have this behavior? So anybody who studied a little bit more deeper magnetism may answer to this. Okay, the answer, of course, is that it lies in quantum physics. Now, all this was done in the framework of quantum physics, this Heisenberg Hamiltonian. It's coming basically from Schrödinger equation. So we are considering here that these spins are coming from electrons, which can be described by waves. So waves are not localized as a particle, let's say, in a certain point in space, but they are extended, and we may have an overlap of wave functions. So if two electrons can be described by two wave functions, then they can overlap. But of course, you can imagine if they are very far from each other, these wave functions will not at all overlap, and we are here in this region. And so exchange will be 0, and we don't have magnetism. If they get closer, then you will have an overlap of wave functions. If they get, however, very close, then you have an overlap of wave functions and complete overlap of wave functions. But what does that mean? If you have a complete overlap of wave functions, then electron spins are not free anymore to align. They cannot align parallel, let's say. They have to align antiparallel, as it happens here in manganese, for example. Why is it like that? The reason is Pauli principle, of course. Pauli principle we will see later. As a nice example here, I show you that manganese usually is antiferromagnetic, and this is shown here in the beta-Slater curve. But if you add another element like arsenide, then you have manganese arsenide, you will get a ferromagnetic state because you increase the interatomic distance, and in this way, the spins can again align parallel. Okay, so Heisenberg exchange. How can we derive Heisenberg exchange? I will not do this in detail with you here, but I will give you the main ingredients for deriving Heisenberg exchange. First of all, it's a quantum effect. We need as ingredients the Coulomb interaction. We need the indistinguishability of electrons, and we need what I already said, the Pauli principle. So let's go through this recipe, let's say, of deriving Heisenberg exchange. So first of all, we have to consider that, of course, electrons can be described as wave functions, and the energy of these wave functions is described by the Schrödinger equation. So Schrödinger equation, I guess all of you already saw this wave equation. We have a wave function. This is, let's say, the equivalent of the kinetic energy. This would be the equivalent of the potential energy. Of course, in this case, it's the Coulomb potential that we have to consider. And then we have the eigenstates of our electron, of our wave function, which describe the quantized energy states of the electron. Okay, let's take a very simple example. We have two atoms, let's say, described by two nuclei, and two electrons, and they are connected with these two nuclear versus via the Coulomb potential. First of all, let's not consider any interaction between the atoms. Then we have two independent Schrödinger equations, two independent wave functions, let's say. And a single atom solution, of course, can be described by a probability distribution. And the probability to find an electron, of course, it's higher whereas the nucleus, and it's decreasing exponentially with the radius far from the nucleus. So if we have two atoms, then we can find two different solutions. So this would be the so-called antisymmetric solution. So if you have an atom at the position or an atom at the position R, you can have this probability distribution. You will find that exactly in the middle between these two equal atoms, you have zero probability to find an electron. In this case, this would be called the antibonding state. On the other hand, you can have this combination of the wave functions, and you will find that here in the middle you have a probability to find electrons between the two atoms, and this is called the bonding state. So this would be an antisymmetric spatial solution. This would be a symmetric solution. And now we already apply, of course, then the Pauli principle, because you know probably from your studies that in the bonding state, of course, this is a symmetric spatial solution. You have to fill in the electrons in an antisymmetric way, so with spin up and spin down, while in the antibonding state, you can fill them also parallel. However, the total energy is given by the energy of the single atom solution plus or minus this energy of the bonding. Okay, Pauli principle, as I told you, in the antisymmetric spatial solution, we fill in parallel electrons, so a symmetric spin state, while in the symmetric spatial solution, we fill in antisymmetric spin states. Now, what else we have to consider are the interactions. So interactions we have to consider, first of all, the Coulomb interaction in a single atom here. So the nucleus A with the electron A, the nucleus B with the electron B. The Coulomb interaction between the same charges, so between the nuclei and between the electrons. And something more, you have still to consider that this electron could be also part of the electron B, could be part of atom A. Nobody tells me which electron is part of which atom, because electrons are indistinguishable. So this is the fact that I told you at the beginning, because electrons are fermions. Now, considering all this kind of interaction, then you can derive an Hamiltonian, energy Hamiltonian, which will describe the energy states of these two electrons in the, with these two atoms. And you will find this Heisenberg Hamiltonian here, which is part of the total exchange energy. So this was a very simple recipe, let's say, how you would get a generalized exchange Hamiltonian. Of course, the calculation itself is from The principle is very simple, but the calculation is a bit long. You can do that if you're interested in this. It is described in many, many books. Now let's move from ferromagnetism to antiferromagnetism. I already told you that it's just, it's the same force, let's say, the same principle, but antiferromagnetism, of course, causes a net magnetization that is zero. And it's given simply by this J negative and an anti-parallel configuration of spins in a magnetic moment, of the same magnetic moments, of course. You can describe this also classically by Weiss theory, taking equivalent sublattices, for example. Of course, you may say, and also it was a bit like that, considered that antiferromagnetism, rather from application point of view, rather useless almost, because you can imagine we have a strong exchange interaction in the material, but magnetization is zero. So this also means that the influence of magnetic fields is almost zero, and it's also very difficult to measure antiferromagnetic materials. So for a very long time was not considered to be that important. However, this changed now in the last years dramatically, and there's a very big attention of the scientific community to antiferromagnetic materials. And one example, you can also give a look to these links that I put here. One example is magnetic memories. So focus one of the applications of magnetism are hard disks, for example, and where you have the information stored in single small bits on your hard disk. Of course, if you want to increase the energy, the storage density, then you have to reduce the single bit size. But you can imagine that if I reduce the single bit size and I also bring them very close together, the single bits, then they will influence each other. So each of the bit will have a magnetic field, let's say outside, which will influence the second bit, as shown here in a ferromagnet, for example. Instead, this is not the case in the antiferromagnet. One could imagine a single bit magnetized, let's say horizontally or vertically, no? If you like. In this case, the magnetic field outside is always zero and will not influence the next magnetic bit. And you have to read them simply by the direction of the magnetization. So this, which is perpendicular to each other. So this is a very elegant way to use antiferromagnetic materials, and that's why it's becoming so important. Another special case of ferromagnetism is ferrimagnetism, let's say of antiferromagnetism, because it's a kind of antiferromagnetic exchange. So we have the exchange constant is smaller than zero, but now we don't have the same magnetic moments as in antiferromagnets. We have that one magnetic moment is stronger than the other magnetic moment. And in this way, you get the total magnetization. So it's not zero anymore. But of course, you can imagine it's much smaller than in a ferromagnetic material. And classical examples of ferrimagnets are ferrites that I already mentioned, so oxides of iron. And here we usually have, for example, here in this kind of ferrite, you will have different oxidation states, and therefore you'd have different magnetic moments, as I showed you before. We have 3+ has 5 μ Bohr, while 2+ has 4 μ Bohr. as magnetic moments, and the total magnetic moment, of course, if they point in different directions, will be the sum of all, the subtraction of all magnetic moments. Okay, so until now we were speaking only about direct exchange interactions. So we were thinking about these two spins S1 and S2, neighboring spins, which are localized at an atom at a certain position in the crystal, for example, and you may have an overlap of wave functions up to a certain extent, and this will describe your antiferromagnetic or ferromagnetic behavior, or it will describe if there's no ferromagnetic behavior. So then we speak about paramagnets. So direct Heisenberg exchange requires the overlap of wave functions. We saw this before, no? Otherwise, we would not have any Heisenberg exchange in the derivation of exchange interaction. However, in many materials, we don't have a direct overlap of wave functions. And nevertheless, we can have exchange interaction. This can be a kind of indirect exchange interaction. And one way to have it is, for example, the so-called super exchange, which happens exactly in ferrites. So when you have an oxygen ion involved in your crystal, because the oxygen ion will mediate the spin information and will transport the spin information from one ion to the next ion. And you can see here the 3D orbitals of iron and the orbital of oxygen. And you can see if you have an overlap between the oxygen and the iron orbital, then the spins will align antiparallel according to the Pauli principle. And this will lead to an antiparallel alignment between the two iron ions. So this is necessarily an antiferromagnetic exchange, super exchange. Another possibility to have an indirect exchange interaction is the so-called double exchange, which we have in manganites. And here in manganites, very often you have different oxidation states, but they very often introduce holes. So you have a different oxidation state as a, let's say, almost a defect in the lattice. And if you have an electric hole, let's say, then you can have also hopping of electron. And this electron will transport its spin information from one ion to the next ion. And in fact, these kind of materials, one example is lanthanum manganite. These materials very often have a metal insulator transition also. Not only in oxides, we can have indirect exchange interaction, we can have this also in metals. And this depends on the fact that the spin can be transported also by free electrons. One of the very important indirect exchange interactions is the RKKY exchange interaction. That has this name due to the 4 scientists that studied this kind of exchange interaction, which were Ruderman, Kittel, Kasuya, and Yosida. And this was found in 1963. So this is very important in lanthanides, in the so-called 4F metals, 4F elements, because in 4F elements, we don't have a direct overlap of orbitals, because the 4F orbital is very much localized to the nucleus. So while you can see here the distance between two atoms would be 1.8 angstrom, the orbital is only of 0.5 angstrom. So there's in fact no direct overlap. However, we have exchange, and this is by the free electrons, the conduction electrons in the material. The very nice thing is that if you plot the exchange constant with respect to the distance from the localized moment, then you will find that this exchange constant is oscillating. Especially is oscillating from positive to negative values. So according to the distance between the localized moments, you will have parallel alignment or anti-parallel alignment. So this kind of exchange interaction in the 60s was, of course, very much studied, but it was considered to be something not important for applications. While in spintronics, we had a real boom again with RKKY interaction, because there is happening something very similar to this RKKY exchange interaction, which is the basis for many, many effects that we study in spintronics. And we will see this in the last lecture, the importance of this RKKY exchange interaction. Okay, this brings us to itinerant magnetism. And don't worry, we should be very close to the end of this very, very long lecture. Why itinerant magnetism? Now we said, okay, in RKKY you have localized magnetic moments, and the exchange is mediated by these free electrons. And effectively, this is also the case in iron, nickel, and cobalt, in the 3D elements, but not through an RKKY exchange mechanism, but to what is called itinerant magnetism. So why? Because actually, also in iron, nickel, and cobalt, there's almost no overlap between the orbitals. So we cannot describe magnetism in iron, cobalt, and nickel by the classical Heisenberg type of exchange interaction, because this would require the overlap, of course, of wave functions. One point that was puzzling immediately the scientists was the fact that, in fact, in these materials here, in these elements, metals, the number of magnetic moment per atom is not an integer number of mu Bohr. So if you remember in the example that we did with the iron ion, there we always had an integer number times mu Bohr per ion. And this has to be like that, because we can always have only a combination of elementary magnetic moments, no? If they come from the S state, for example, then we should always have an integer number by mu Bohr per atom. In iron, instead, we have 2.2 mu Bohr. If you calculate coming from the magnetisation, total magnetisation of a piece of iron, you calculate the number of magnetic moments per atom, you will get 0.2. In cobalt, we have 1.7, and in nickel, we have 0.6. So this fraction of magnetic moment per atom sounds a little bit that different atoms divide among them the magnetic moment of electrons, for example. And this brings us, of course, to the fact that free electrons or conduction electrons in metals have to contribute somehow to magnetism. And in fact, localized moments couple to itinerant conduction electrons through the 3D 4s interaction. And this brings us to band magnetism. So band magnetism is demagnetism in conductive materials, let's say, where magnetic moments are not localized but transported. So one of the examples for magnetism that can happen in systems with free electrons, and here we are considering completely free electrons, let's say, is paramagnetism, and this is the so-called Pauli paramagnetism. So we have to understand first Pauli paramagnetism in order to describe then ferromagnetism of free electrons. So considering now this is just a summary of what you studied in solid state physics, since electrons are fermions, they will fill up all energy states up to a certain Fermi level. Of course, all states can be filled up by spin up and spin down, and we have a density of states, which is proportional to the square root of the energy. Considering this density of states and considering the two spin states, I just plotted it here. Usually we have equally filled with spin up and spin down. And we have this energy distribution. If we apply instead a magnetic field, then you can consider that we apply the magnetic field parallel to one of the spin states, while the other one will be anti-parallel. And this means that this energy of states will be shifted. So the parallel ones will be shifted to lower energy states, since we have to add the contribution of the Zeeman energy here, while the antiparallel will be shifted to higher energy states, always due to this Zeeman energy of a magnetic moment in a magnetic field. And in this way, you can see these two energy of states are not compensated anymore, and you will have a net magnetization. Net magnetization you can simply calculate. I will not go into details now here because it's already very late. From this slice that is shifted, very simple calculation, and you get the net magnetization, and you also can derive then the susceptibility. And the susceptibility, the so-called Pauli susceptibility of paramagnetism, is proportionate to the density of states at the Fermi level, at the Fermi energy. Now let's apply the same concept to ferromagnetism. And this is the so-called stoner ferromagnetism, always of free electrons. As we said before, ferromagnetism always requires a spontaneous alignment of magnetic moments. And here we have a spontaneous splitting of these two spin up and spin down subbands without an applied magnetic field. First we had it proportional to the applied magnetic field. Now we have it without an applied magnetic field. And why is it like that? Again, here Pauli principle plays a very big role. So Pauli principle tells us that two electrons with the same spin can never be in the same place at the same time. But this means also that electrons with opposite spin can get much closer to each other. And if they get much closer to each other, they will feel a stronger Coulomb repulsion. So this can be energetically not favorable. So if you have the same amount of spin up and spin down electrons, the energy due to the Coulomb energy might be quite high, depending on the material that you have. And in certain materials, it might be favorable to shift a certain amount of electrons to the opposite spin state. So you have this spontaneous splitting as indicated here. When is this spontaneous splitting convenient? And this tells us the Stoner criterion. it's convenient if I times n, the density of states at the Fermi level, is larger than 1, where I is the Stoner interaction energy constant. Two difficulties about this Stoner criteria, about this Stoner theory. Stoner theory describes very well the fraction of Bohr magnetons per atom in metals, but it does not, for example, describe well the temperature dependence. And another difficulty is to evaluate this Stoner interaction energy constant I. It's difficult to find from theory. Okay, with this finally, I'm at the end of my lecture. And you can see here the questions that I will ask you in the next lecture. Please give a look to them. Maybe we can quickly answer to them in the next lecture. And if you have, of course, some questions, so please ask them. Here you find indicated the chapters of the book of Blundell that I used for preparing this lecture. Stefano, are there cases in which the orbital magnetic momentum instead of the spin magnetic momentum plays a significant role in ferromagnetism? You mean in the way that it's more important than a spin magnetic moment? Actually, according to what I know, usually the spin magnetic moment is playing a more important role. I don't know if Vittoria has an idea.
Well, there are a few rare earths where the orbital moment is important. So within the series of the rare earth, you have this combination on spin and orbitals. So, for example, those that have large spin, for example, gadolinium has the largest spin with 7 electron aligned. But there are other elements, as far as I remember, I think holmium, all of them, where the total magnetic moment is very large and is due to the combination of the orbital and the spin. So why we don't have materials, magnetic materials with this holmium or whatever? This could be a question you could make, Michaela, after your lecture. No, it has to do with the strength of the exchange. So you may have a large atomic moment, but then the aligning interaction is something else. Stefano, comment. You want to read, Michaela?
I think that is due to the fact that in rare earths, the JJ coupling is more important than the LS coupling.
Well, there is one rule, no? Exchange has to do with the spin and not with the orbit. So you may have a material, in principle, because then I don't know. No, probably no. But in any case, you have a combination of both spin and orbit as angular momentum. And they combine for having a total magnetic moment to the atom. But then it's only the spin part that gives rise to exchange interaction. And in most of the rare earths, the exchange, as far as I remember, is negative. So they anti-aligned. But these are very specific cases. So LS coupling, as Michaela said, is very strong. SS coupling between different atoms. Can be strong or not, but generally it's not that strong. And we will say something when we discuss the permanent magnetic materials. No, when you have not only the rare earths, but you have also transition metals.
What I said in the lecture now was exactly this. In the rare earth now, very often you have these localized orbitals, and you don't have a direct overlap of wave functions, and you don't have Heisenberg exchange, no? And that's why, you know, they came up with this RKKY, because this was studied exactly in rare earth very much, no? Because you don't have, no, this direct overlap. So for this reason, no, ferromagnetism, however, may be weak in these materials. But what they bring with a strong L, and this helps us a lot, no? For example, is anisotropy, magnetocrystalline anisotropy. And very strong magnets that we have are usually a combination between 3D elements and the 4F elements. Because you get the 3 element for bringing in the Heisenberg exchange, and then you bring in the L due to this 4F elements. So in the sense, a strong magnetization, usually you don't get from the L contribution, at least as far as I know. Okay, something else. I just wanted to say something for the organization of the course. It might be that I have problems to give a lecture on Friday morning. It's not fixed yet, but would it be possible for you, maybe I write also an email then, to have the lecture on Friday afternoon, as we had last Friday at 2, Vittoria, also for you, if it's...
Yes, for me it's okay.
Okay, so maybe I will write an email about that. I will confirm you this change of lectures on Wednesday, let's say. Okay. So now we want to have a short break. Let's start at 10:40. What do you think, Vittoria?
Yes, it's okay for me.
Okay.
Maybe 45. What do you think? We give a break. I probably managed to stay in time. 10:45. Now it's already almost 30.
Okay.
Okay, thank you everyone. Yes, now we are recorded. Okay, so welcome back everyone. This is the second part of lecture 3. So we call it Unit 3.2. So after the overview of Michaela, quite detailed view, I would say, not only overview, on the microscopic atomic quantum mechanism of the formation of the atomic moment and the causes of exchange interaction in matter. Now we go back to, in a sense, macroscopic and continuum description. Again, and in part in terms of Maxwell relations, and also something else. So, as you have seen, we keep these two parallel tracks. One that is trying to push, as far as it's possible, the theory of continuum, in a certain sense, description of magnetic materials, and to see how far we can go. And actually, we can go quite far. Also taking some of the results from quantum physics, that actually we are able to go and to build up quite good descriptive theory for ferromagnetic materials in terms of continuum description. And sometimes we keep some results from quantum physics, let's say. This we discuss in detail. So let's say the plan essentially of the first lecture I'm giving is to prepare the path to arrive at this continuum description of ferromagnets. And we have seen Maxwell equations, we have seen magnetostatics, and now we touch another quite delicate point, which is energy relations. We have seen the description contained in Maxwell equation is essentially a description of field, electric field and magnetic field, and together with their sources. Then we had to adopt the Ampere hypothesis in order to include magnetic material inside the description of Maxwell. And we have seen that the adoption of this hypothesis, which in a certain sense is like to hide somehow the quantistic and quantum origin of magnetism, is not that wrong. No? So we can proceed by essentially describing material in terms of density of magnetic moment, essentially introducing the magnetic moment as a quantity. So with this density, with the magnetization included inside Maxwell equation, we can describe both the magnetic field generated, let's say, under our control, generated by our currents, by our solenoids and whatever, and the magnetostatic field generated by the magnetized matter itself. But now this is not enough. So as we want to learn something about this will not be done in this lecture, but in the next one, on the energetics of a ferromagnet, we have to deal into some detail with the energy contained in Maxwell equation. So how to describe the energy of the magnetic fields, also considering that we have included magnetized matter in Maxwell equations. And in order to arrive to let's say, an energy function for the ferromagnets, we also touch thermodynamic relations. So in a sense, it's a generalization of these energy relations. So please follow well, because all the concepts that we will touch here are quite delicate. And I also want to start with a question now, a question that looks really obvious, because we have seen that we introduce magnetized matter thanks to this magnetization vector, and this magnetization vector is nothing else than the density of a magnetic moment. So we have this magnetic moment, which is the quality of a piece of magnetic material let's concentrate this piece in a point and that's it. But we generate magnetic field in space. So let's consider that these two objects. One is a piece of magnetized material. That is described by its magnetic moment. I use the letter mu. It is a vector. And then we have some external field generated by our solenoids or whatever. So this is my question, no? This is the question for us. What is the energy of a magnetic moment in an external field? So I propose to you two different answers. Well, it will be the product. So the product that I wrote there. So it's mu0 times mu, which is the magnetic moment, times the applied field, external field, the one generated by the solenoid. So should I put the sign minus or should I put the sign plus to get the energy of a magnetic moment? I would like to try to make your guess. Please. With the plus or with the minus? And also if you want to say why, it should be one or the other. Any guess? Don't be shy, because don't be shy for a reason that you immediately get. No one can want to try? Stefano, you always participate, so you want to try yourself? Yes, the minus sign, so you remember well. But there is someone for the plus? Or everyone agrees with Stefano? You all want the minus, or there is someone for the plus? Someone for the plus 1, 2, 3. No one for the plus. Oh, come on. Okay, so, well, the point is the following. The answer of Stefano is clearly the correct one for magnetic materials. This is the expression that we use all the time. And why is the expression that you use? Because this is also the common, it's perfect agreement with the common sense. So think that the magnetic moment is nothing else than a compass needle. Then the compass needle will will try to align with the field. So in order to align, if you think about of energy and the process of the rotation of the compass needle as an energy minimization process, then in order to be the minimum, the mu has to be parallel with H, not anti-parallel. So the common experience with the magnetic material is that the green formula is the correct one. The magnetic moment would like to be aligned with the applied field that is found there. But if you take it in more detail, you discover that the Maxwell equations themselves, they do not predict the green solution, but rather the gray one. If you take Maxwell equation, the correct expression of the energy is the second, not the first. And why? Because in Maxwell equation, you don't have any compass needle or permanent magnet there. You have only currents. So if you think that the energy is contained, an energy description is completely contained in Maxwell equation, then is the second that you will derive if you take just Maxwell equation alone. The point is the following, that the two have a completely different meaning. The first is the energy computed as you have a permanent magnet already built up and permanent, so you cannot change it. It's regardless if it's made of spin, if it's made of an electric current or whatever. But in a sense, the description of the magnetic moment is outside the Maxwell equation themselves. If you take such a magnetic moment and you bring it into a field, then it's the energy that you will have to spend or that you will have to gain. Bring it parallel and then you gain some energy. Bring it anti-parallel and then you have to spend some energy. But if you take Maxwell equations themselves, there is no magnetic moment in any place. So the energy, you have to build it. You have to use the field in order to build the currents. And then in that case, that is the energy that you have to spend. You have to spend energy in order to build a magnetic moment which is parallel to the field in that place. So I make this comment and they spend some time because this is touched very, very, very briefly in the books. So you find it very clearly explained in the book of Jackson. But otherwise, most of the books on magnetic material, they take the first expression as for granted. If you take a book on electromagnetism, they take the second expression for granted. So please use some care. We have always to take care if you don't specify well what is the problem we have to deal with. So we will select the first systematically and always. So in a sense, we are not interested to all the problems in which the magnetic moment is formed by Maxwell equations themselves, because we want to deal with magnetic material. So we have magnetic moments already there. In a certain sense, it's like we take this from quantum physics. The spin is already built up in the nature of electron. And then we have this as a magnetic moment, in a sense, permanent. Taking if you like to have an explanation like this. This is very nice because, this we said already. And this is very nice because then this is the starting point, in a certain sense, of our description of energy of a magnetic moment. The energy of this moment is the expression written there. But then we can also derive the possible mechanical torque on this magnetic moment. The torque that will be experienced by the magnetic moment itself as an object, it will be the external product of the magnetic moment times the external field that you have in space, without considering the field generated by the magnetic moment itself. This torque is important because torque acts on angular momentum, and we will have a lot of consequence of this relation here, of having a mechanical torque generated by the external field on a magnetic moment. Well, if you have a compass needle, then this is clearly the force which is trying to align the needle with respect to the field. But there are other more important consequences of this, because not only you may have the angular momentum of an object like a compass needle, but you have the angular momentum of the atoms of the same angular momentum which is generating the magnetic moment that will feel a torque due to the presence of the external field. So this is an important fact that for the moment we put aside, but just remember that the fact of having a mechanical torque on a magnetic moment will generate an effect that we will know as precession of the magnetic moment that we will see later. And this is extremely important, especially in modern application of spintronic or magnetic memories. So effects that will be important and valid at the gigahertz range, not in static, not very much in statics. So for the moment, let's leave it there. This is an important starting point. The torque will act on the angular, the total angular momentum. So this will include also the spin, if we have the magnetic moment generated by the spin. Let's make another step, and let's make another question. So again, if you like to try to answer. So we mentioned about the energy of a magnetic moment inside Maxwell equation, or in general. I've not specified the question. That was the problem there. But here I try to specify in more detail. And this, if you know electromagnetism, maybe you can remember something, or some important relations contained in Maxwell equation. That tells us about energy conservation within Maxwell equations. So if you remember, what is the energy relation that we do have in Maxwell equation, and very often we see in books? Do you remember the name of this energy relation? It goes into the name of a person that stated a theorem on this, and it's not Maxwell itself. Do you want to guess? Do you remember? It has to do with electromagnetic waves. So for those that knows a little bit about the transmission of electromagnetic waves, for sure they know the answer. You want to try to put something on the chat? Pointing theorem, yes, exactly. Is exactly the pointing theorem, a relation between the fields and the sources contained in Maxwell equation that can be demonstrated from Maxwell equation. And it is a relation that contains the energy conservation, which is implicit in the statement of the Maxwell equation. So let's spend some time, because the theorem itself looks very ugly in a sense. So let's spend some time to understand what does it mean. First of all, the system that we have in mind is always something that contains current flowing, possibly charges. I have also put in the picture a battery, so a generator for this current, because now we want to deal with energy. So we want to know where this energy comes from. And I've also put that squared that now looks not so nice, which is the permanent magnet that we are interested in. So the pointing theorem is written here in differential forms, but then we will try to integrate it. What do we have? On one side, we have the product of the electric current density times the electric field. Then the electric field times the derivative time of the electric displacement, the magnetic field times the derivative time of the magnetic induction, and at the right-hand side, we have minus the divergence of a vector. This is very often called the pointing vector. So the external product between H and E and H. The good thing is that we have a divergence, so we can do more or less the similar thing we have done at the beginning with the electric field. So in the equation with the electric field, we had the divergence of the electric field, and then we could demonstrate that instead of making a volume integral, we could make a surface integral. And surface is really what we like, because we want to see how energy is conserved, where it's coming, where it's going, and especially we want to know if there is some energy flowing out of the volume that we are considering. So let's take the pointing theorem, let's take our system, and let's define a certain volume. So we enclose the system containing the generator, the current loops, the permanent magnet, and we define this as our volume with a certain surface. And what do we plan to do? We plan to integrate over the volume all the terms at the left-hand side and do the same for the right-hand side and apply the Gauss theorem. Therefore, we can transform the integral over the volume of the divergence into an integral over the surface of the normal of that vector of the surface. So we compute the flux. But this flux now is an energy. This is very nice because this is an energy flux, an energy which is flowing out of our volume. This energy is related to the Poynting vector. To do this, however, we need something else. As we said, to complete Maxwell equations, we said we need constitutive equation for the material, no? For the magnetic material, for the dielectric material, and so on. We don't want to care about dielectrics, so we just put the displacement vector equal to 0, and so we completely neglect. We neglect charges, so we don't have free charges around. We only have electric current. But we have put also the generator inside the volume. So what we have to specify is the relation between the E field, the electric field of Maxwell equations, and the electric current. And this is well known as the Ohm's law. But we have also put inside the generator, no? A sort of a battery. So how can we have a current flowing only for the Ohm's law? It's impossible. So we have to make a sort of generalization of the Ohm's law. And what is needed is what is written there. So to describe the flow of the current in our circuit, we have also to introduce what is called a sort of a fictitious electric field, E prime, that describe the fact that we have some chemical energy inside our volume. So when we have the circuit which is shown there, so this energy barrier with the current flowing through the loops, then, okay, the current density J will be given by the electric conductivity of the wire times the electric field inside the wire itself. But when it's inside the battery, we need some mechanism that is taking our electron, our charge, and which is in a low potential state, and is taking it up in energy. So taking it again at a large potential, and then have the continuously flowing current. This mechanism needs something else. So we need something which is not contained in Maxwell equations themselves. And this is sometimes called E prime. So an electric field that has nothing to do with the Maxwell equation, but comes from chemistry, if we have an electric battery. Or otherwise, if you like, is a way to describe the electric plug where you put your instrument, your amplifier, your generator. So it's something more, something that really describes the energy sources, because at the moment we have no sources there, only that one. We have the source which is letting the current flowing through our coil, let's say. If you do like this, then E, which is contained in the first product, splits in two. One part is just the product of the electric current times E prime. And this is really the source from what we have said now. So we want to put inside the E prime or the chemistry, all the whatever you want, that is a source of energy. Integral over the volume of the electric current density times the E prime. Let's forget about all this and call it an energy source. The energy source that we put at the left-hand side. All the rest we put at the right-hand side. Well, the part that has to do with the Ohm's law itself is energy dissipation. So we can directly express this energy as the current density square over sigma, the conductivity, integrated over the volume. This is energy dissipation. The Ohm's law describes energy dissipation. So we have it's fully it has fully sense to have a term at the right-hand side that describes that some of the energy is dissipated in terms of Joule heating in the wires. But then we have two important terms. First, I described the one due to the Poynting theorem, the one that is transformed the divergence into a flux, so an integral over the volume, over the surface and not the volume. This is the last term at the right-hand side of this equation, this one. And this is an integral over the surface of the Poynting vector, E external H. This is exactly the energy transported by possible electromagnetic waves that we can generate inside the volume. So if, for example, we can switch on the current, switch off, and do whatever we want, we may have electromagnetic waves that are generated in our volume, and they spread out in the space. So they cross our surface and they simply move away. This is, there will be some energy that is transported across the surface in terms of electromagnetic waves. And we take into account, so this is an energy flux that comes from the Poynting theorem. But what is interesting for us is the remaining term, because then we have on the left-hand side the source, energy source. Then we have some energy which is flowing out of the volume, some energy which is dissipated as heat, and the remaining part. The remaining part is the integral over the volume of H dB over dt. This is the magnetic energy. So this is our interpretation from the Poynting theorem. We can derive a term that we have to interpret as magnetic energy. We spend some energy which is going part in magnetic, part dissipated as heat, and part into electromagnetic waves. And remember that we have neglected any polarizable material. So, and if we include also the polarization of material, we would have also some electric polarization work. So we reach very, very interesting results, an expression for the magnetic work. The change in, let's say, in time, let's put out the time there, because we are not interested to essentially times that change, things that change in time, but we can write an expression for the magnetic work as the integral over the whole space. If take our volume and put it at infinity, so every time we have a change in magnetic induction times the magnetic field H, this is a work that we have to spend. And this is the most general expression of magnetic work. It can be valid for both in absence of magnetic material, with magnetic material, with magnetic field generated in space. We have to specify. So we have to specify. What is the plan? So if we want to understand something of the energetics of magnetic materials, then we have to take this magnetic work, that is just from the point of view of engineering. No, this is the work. If I want to build an electric machine, then this is the work that I will spend to do magnetic action on something. But if I want to know the physics of the material, or the microscope, the behavior of the material, then I would like to know how much of this work goes into a magnetic field and how much it goes into the magnetic material. So what is the role played by the magnetized matter in this magnetic work relation? So HDB now try to be put attention on the terms that you will find there in the product of the magnetic, giving magnetic work, because now we will enter its quite confusing issues. But please remember this: HdB is the total magnetic work. Then you will find other things, because immediately things become to be a little bit more complicated. Why? Because we want to take the results we derived the last time and apply also to energy and work. So, last lecture, my lecture, we understood that we could separate the magnetic field into the magnetostatic field generated by the magnetized matter and the magnetic field that is under our control, for example, generated by circuits, by currents that we can generate in our lab. So let's use these definitions, very practical, but sometimes useful, no? to separate the two sources. So again, terminology is not that completely and truly accepted everywhere. And again, let's say we describe quality of this magnetic field that is not fully acceptable as a word. But in any case, let's take a situation like this. We have a current loop or a solenoid, and we call HA, so applied field, the field that we generate with our solenoid system. Let's call magnetostatic field the field which is generated by the magnetic material. It's the object that we want to study, we want to understand, HM. So, as we learned the last time, the two fields are different in sources. For the applied field, we have the currents. For the magnetostatic field, we have the divergence of the magnetization. The total field will be the sum of the two. We have two different sources. Okay, so now, if we have to spend work to magnetize, magnetic work, for sure we have to spend the work to generate applied field. But we also have to spend the work to generate magnetostatic field, because if this applied field also magnetizes the magnetic material, the magnetostatic field will change. And who will pay the price? Again, it's due to the battery. So there will be some energy source of this energy accumulated in the magnetostatic field. And then, if I know the energy accumulated in the applied field and in the magnetostatic field, there is something missing. There is some work that goes only into the magnetic material. So there is some internal energy to be associated with the magnetic material or not. Well, we will discover, because we have the total work, total magnetic work, and we can compute from Maxwell equation the energy to generate an applied field and the energy to generate a magnetostatic field. So the plan is the following. Let's compute the work to generate the applied field, the work to generate the magnetostatic field, subtract both of them to the total, and discover what is the internal energy. And this is very interesting, because we can understand how much it goes into Maxwell things and how much it goes into something else that we don't know yet and we would like to discover. So let's start to do this. What is the energy of the applied magnetic field? Well, this field is in all space, and the sources are the current. And this is the simple expression. The energy is the square of the applied field multiplied by mu0 and divided by 2, integrated over the whole space. Okay, this is quite simple. If I make just a change of this applied field, so what is the delta, the work to change this field, then I have the expression below. The work the delta W is given by mu0, again integrating the wall space of the field multiplied by the change of the field in any point. So I have both the expression of the energy and both the expression of the work for generating what I call applied, but it's a generic magnetic field generated by current density. Now, if I have to turn to magnetostatic field, sorry, let's make the step, because now, if the total work has to both magnetize the material and generate the magnetic field in space, I can immediately subtract it, no? So I arrive to expression like this. If from the total I take out the work to generate the applied field, I call this magnetization work. Why? Because it's really the work to magnetize something, regardless if then it's going to move magnetic domains, orient the spins in the material, or just generate a magnetostatic field because you magnetize the magnetic material. This is called magnetization work. Magnetic work, magnetization work. In the next, we will try to find expressions for this magnetization work. And to do this, we have to make the other step. So to compute the energy of the magnetostatic field. Again, start from the equation of the magnetostatic field. They are different because now they contain the source. They are, how to say, charge-like, the divergence of magnetization. So the expression of the energy is the same. Okay, we can integrate over the wall space mu0/2 of the magnetostatic field square, and so on and so on. But we can also derive a different expression. Why? Because the sources are limited only to the magnetic material. So there is a very nice expression where we can, instead of integrating over the wall space, express the total energy of the magnetostatic field as minus mu0, 1/2 of the product of the magnetostatic field times the magnetization. Do you remember this expression, minus mu0 h times m? Consider that you integrate the magnetization over the volume, no? So the integral will give a magnetic moment. It looks very much like the energy of a magnetic moment in the magnetic field, no? Minus mu0 hm magnetization. But now there is a factor 2. It is a mistake 1/2, no? So mu0/2. It looks like the energy of a magnetic moment in a magnetic field, but there is a factor 2. Is it a mistake or is it correct? I mean, you would say, if you wrote it, is correct, no? If you want to make any comment, why there is a factor 2 there? Look at the chat, if someone wants to answer. What's the difference between the initial case of the magnetic moment in the magnetic field? Someone wants to try to give the answer? Well, essentially, we said one important thing in passing by, no? At the beginning, we said, well, Stefano, good. The factor 1/2 is necessary. Otherwise, we count twice the work needed to bring the charge from infinity. Otherwise, we count twice. Maybe you could be correct. Essentially, the answer I give to myself when I asked me this question is because at the beginning I said that the applied field is the field generated by all other sources apart by the magnetic moment itself. And here we are exactly in the opposite situation. Here the magnetostatic field is exactly the field generated by our magnetization distribution. So it's the magnetic field generated by itself, by the magnetic moment itself. It's clear that you need, how to say, here the dimension is necessary, no? So you cannot put things to points, because you need a divergence. To have divergences somehow. So the finite size, I would say, in a sense, is necessary. Also because you want to integrate over something. But essentially it's this. So here, this is a sort of self-energy. Is a self-energy. Is the energy of the magnetic field generated by the magnetization itself. And then this factor 1/2 is necessary there. And what is important here is that we were able to show that this integral can be made over the volume. If I have only the magnetization in the volume V, then I can limit the integral to the volume where the magnetization is different from 0. With these results, we can make the next step. And this is very interesting because now we have the work to generate HA. So it's HA times the variation of HA. The work to generate HM, and that I can write over the wall space, and then I don't learn too much. But I can equivalently write it as a volume integral over only the volume of the magnetic material, and then I can write the expression for the magnetization work in a very nice way. So I can write the expression which is yellow there. The magnetization work is one part, the magnetic work, the work to generate the magnetostatic field, and the remaining part is just the mu0 integral over the volume of the field H dm. For this, I said, remember that all expressions of work look similar, but they are all different. So the total magnetic work is the integral over the wall space of H dB. But the integral to magnetize, to the magnetic work turned into internal energy is HDM. HDM. HDM is one of the mu0 HDM. So it's one of the most common and used expression to indicate the work that goes into internal energy. So something that has nothing to do with Maxwell equation. It has to do with internal structure, some energy that is stored into the magnetic material. As I said, as we can also write the work to generate the magnetostatic field. Oh, okay, the result, sorry. I was anticipating this thing. So the work toward internal energy is only the integral volume of the magnetic field, total magnetic field, over the times dm. Or even I can also make another expression at this point of the magnetization work, now using not the total field, but only the applied field. So look at this very nice expression. So the magnetization work, so if you take the applied field times dm, you get the magnetization work, so the total one, both to magnetize the material and to generate the magnetostatic field. If you take HDM, you get only the part which is converted into internal energy. This difference between the two can be huge, because you can, as we learned in the previous lecture, we can think of systems where we generate the magnetostatic field or not, because we have seen that this depends on the shape of the magnetic material. So if we close the magnetic material or the magnetic flux in a ring, then we don't generate a magnetostatic field outside. Otherwise, if we leave the magnetic material open, in a sense, then we will have to generate the magnetostatic field. Let's see an example of this difference, because this is very nice. So, and the example is the following. So let's take a magnetic material, a ring, no? And let's wind let's wind the current wires around it. No, so on these windings, we let an electric current flowing, so we can generate an electric field which is able to magnetize the material. So in this very first case, and this is this one, what do? We can measure the average magnetization along the circuit, along the ring, and we can easily derive the applied field, as we know the current, so from Biot-Savart law. If we, for example, measure experimentally, quite easy to make something like this, we have the magnetization as a function of the applied field. And we also know that the magnetostatic field is zero. So what happens is that the magnetization work, HdM, is the shaded area. We integrate, so we start from zero, we magnetize the material, and to do this, we have to spend energy, no? We have to spend work. And this work is exactly the shaded area. This work, as we said, the integral, in this case, in this specific case, the magnetostatic field is zero, and the total work spent goes into internal energy of the system. So it means that it's not easy to magnetize. We have to give to the material, to the magnetic material, some energy, no, in order to stay magnetized. It doesn't want. So, for example, this could be the case of a typical soft magnetic material where you have to give it a certain amount of energy for the domains to get aligned in a certain direction. For example, against magnetic anisotropy. Very, very nice case. But what happens now if we take exactly the same system, but we cut out a piece of magnetic material of the ring? Now it means that the magnetic flux is no more closed in the circuit. Or, if you like, we will have a strong divergence of the magnetization at these two poles here. Or we can generate we have to generate a lot of magnetostatic field. The material itself, it has to generate a lot of magnetostatic field in the gap in order to close the B. And then do the same thing, apply the field, measure the magnetization, compute the magnetization work, and you will find it much, much larger than before. And why is larger? Because the difference between left and right is that at the right-hand side, you have also to include the energy of the magnetostatic field. So there is nothing intrinsic. It's not that the material is different. The material is exactly the same. The energy needed by the material to magnetize is exactly the same. All the rest is the magnetostatic field. The energy that, in a sense, we have stored is much larger. We have stored the energy in the gap, in a certain sense. This is the typical magnetic circuit, where we have concentrated the flux into a gap. But to do this, we have to spend energy. So if you have a gap, you have to include this magnetostatic energy into the magnetization work. Again, so we are, in this sense, we show that the integral of HA, so the applied field times the magnetization, gives the total magnetization work. So it's up to you to know what is the circuit. So how much it goes into magnetostatic and how much into internal energy. Okay, once we got this, we could stop for a moment. So if there are questions, you can also, on this subpart, you can ask it here, because then we take some of the results, and we proceed in discussing a few thermodynamic relations. So if you have a question on what we did up to now, you can also ask it here or at the end if you like. So why we would like to discuss thermodynamic relations now? Well, we have learned that this issue of magnetostatic is very delicate. No, so it's quite also specific to ferromagnets. In thermodynamics, let's say, we would like to extend essentially this notion of system, this notion of work, also to temperature effect. But in general, what we want to import from thermodynamics into our magnetic treatment of magnetic material or ferromagnets is essentially the idea of what the system is. And what the system is something which is very well defined in thermodynamics. And here, specifically in magnetism, we have to take a lot of care about that. Well, let's review for a moment what are the, let's say, basics of thermodynamics, no? And including magnetic quantities too. What I describe here is essentially what is known as key thermostatics. So a theory of, let's say, the equilibrium theory of thermodynamics, where essentially you make the following super simplifying hypothesis. The fact that there exists an internal energy of the system, and this internal energy of the system depends essentially and also only on the extensive variable. And the extensive variable are a list of quality of your body, of your system, that have the property of being extensive. So if you double the size, you double also the variable. Energy is extensive. The volume could be extensive. The magnetic moment is an extensive quality. I double my material and I may have a double magnetic moment. The entropy is also extensive. So entropy is the way we describe heat phenomena in thermodynamics. But it's an extensive quantity, exactly like all the others. These extensive quantities have a lot of important features. They can flow, so we can have an energy flow, entropy flow, volume flow, a little bit different, but you could also think of material that is, quantity of material that is going out, magnetic moment. At the moment, we are not interested of things flowing, but we are rather interested of defining a certain system with its internal energy as a function of its extensive variable. So why the thermodynamic description is important? Because, let's say, this theory is completely axiomatic. So what you assume is that this external energy exists. But if we have this internal energy, then you define all the rest. And the definition is essentially the associated intensive variable. And associated variables are defined as derivative of the internal energy. So if I take one system and I change a little bit the entropy, how big is the change? Well, this depends on another quality, which is called an intensive variable. That is, in case of entropy, the temperature, the absolute temperature. Absolute temperature is how internal energy changes with the entropy. The pressure, minus pressure, is how the internal energy changes with the volume. And also we have the magnetic definition. Now, magnetic field is defined entirely as thermodynamic quantity. The magnetic field is how internal energy changes with the change in magnetic moment. These are called conjugated thermodynamic variables because the product of one extensive and one intensive gives an energy. So entropy times temperature, pressure times volume, mu zero magnetic field times magnetic moment. They all give an energy, total energy in this case. This is Gibbs thermostatics, so axiomatic way to see thermodynamics. But how to use this? Well, we very unusually know how much the entropy of a system is. The volume we can better control. The magnetic moment is something that is not really under control. So there are a lot of cases in which it is much easier when we make experiments to not control the extensive variable, but to control the intensive one. Because, for example, if you take a body and you put it into a thermostat, then it's very easy for you to control the temperature, the absolute temperature. Volume and pressure, it's up to you. You can both control both of them, one or the other. The magnetic field, it's very easy to control the magnetic field, or at least the applied magnetic field. If you take your body and you put it in a region where you control this field, for example, with a solenoid or with an electromagnet. So, in a lot of cases, it's not a good choice to have extensive variables under control, but we would like to have intensive one. And to do this, so to transform thermodynamics, which is a theory for the internal energy, into cases where are the intensive variables that are under control, we have to introduce different potentials. So what are called thermodynamic potential, that are not the internal energy, they are something else. So, for example, let me skip that one and return better later, because now I've started to discuss this, and it's better to proceed in this way. For example, the free energy. The free energy is a functional which is related to internal energy, but it's the internal energy minus the product of temperature times entropy. So if you, instead of the internal energy, you take the free energy, then you arrive to these definitions. The free energy is a function of temperature, of volume, of the magnetic moment. So temperature has taken the place of entropy as a free variable. But this means that we have, again, relations involving entropy. So if we have the free energy, its derivative with respect to temperature will give us entropy, and so on. What is important, if we also want to change let's say, the variable with which we can easily perform work. And these are, well, the volume, but specifically the magnetic moment. The corresponding potential is called the Gibbs potential. So the Gibbs potential, where we control the absolute temperature, the pressure, and the magnetic field, will be given by the free energy minus mu0 h mu plus PV. With this Gibbs potential, then if we know the Gibbs potential, the derivative with respect to temperature will give minus entropy, but what is important to us is that the magnetic moment will be given by the derivative with respect to field of the Gibbs potential. Very nice. So we can possibly compute a relation between the magnetic moment, or the magnetization, if you like, and the applied field. And the field, sorry. I said applied field because now I want to return 2 slides back and discuss a little bit this. Because you may say, you have introduced the magnetic field, then you have introduced the applied magnetic field, then you talk about the magnetostatic field. But in thermodynamics, which is the field to use? As I want to use a thermodynamic relation, so this is written in terms of internal energy. If I perform work on a magnetic field, what should I use? Well, this all depends on what you consider as a thermodynamic system. If the thermodynamic system is the magnetic material only, so you don't care about the energy spent to create the magnetostatic field, then the work term that you have to put is HTM. It's clear. This is the most correct way to do this, because it just means that the variation of internal energy is just mu with respect to the magnetic phenomena is mu0 HTM. This is exactly the result we have derived before. So the part of the work which is converted into internal energy. But you may say, if I'm not able to control H, because, for example, there is no way to do it, I have an open circuit, I control not H, but I control the applied field, because I make the experiment under my solenoid, then I can use, not only have to use the relation, but I need to redefine the system. So I have to say that my thermodynamic, so my description, is in terms of my system plus the magnetostatic field. But then the energy relation has to be written this way. So has to be written with the total magnetization work, HA, applied field, dm. And this means that inside the internal energy, you also put the energy of the magnetostatic field. So this has to be discussed case by case. So it depends very much on what you need to do. If you can control H is one thing. So if you cannot, so you can only perform the experiments where the applied magnetic field is controlled, then you need to define the system in a different way. Let's make the final step, as it's always time to finish. And our final step is, let's say, extend a little bit our thermodynamics of equilibrium. Why? In this we need, because most of the magnetic system we will deal with will have hysteresis processes. So every time we perform any process, a thermodynamic process like magnetizing or whatever, this also will correspond to dissipate some energy. So the second step that we make now is to introduce also energy relations where part of the work is dissipated. This is, let's say, a branch of thermodynamics which can get really complicated. But in a certain sense, we can describe it quite in simple terms. Well, we have to abandon the idea that all the processes are at equilibrium, and therefore the entropy will increase systematically, because we have to apply second principle. But second principle can be quantified. So we can say that the entropy, which is generated in any reversible process, will be produced with a certain entropy production rate. No? So this is a sort of way to describe the energy which is dissipated. So apart from the basic and specific discussion around second principle, which is nothing else to say that some of the entropy is always produced, in terms of the energy, we only have to remember, if we don't go too much into the details, that we have always to account for terms that take into account that this dissipated energy exists. So all these expressions written here are essentially the energy conservation, or if you like, the energy conservation minus the part which is dissipated. So if I perform work on a magnetic material, not all the work will go into internal energy, but part will be dissipated. So we do expect then, for example, if we magnetize a magnetic material, not all the work that we spend will go to internal energy, and we will have also heating losses. So this will be important for in several, let's say, discussions related to the behavior of soft magnetic material, where this dissipated energy is important to account. The last step is the following. So we still consider another step in thermodynamics, and we also, well, first we have considered systems that are at equilibrium, and evolve as a sequence of equilibrium states. Then we have also considered that we may have processes that are not equilibrium, so we dissipate energy. But we may also consider, again, always in terms of thermodynamics, cases where the system is not at equilibrium at all. So we are not in equilibrium state. And again, this is the case of ferromagnets. So what is the, let's say, formal mathematics, let's say, the tools, no? The physical and mathematical tools that we have at hand in this case? This goes into the name of Landau free energy. So the point is the following. In thermodynamics, potentials are global free energy minimum. So we don't have to say too much about them. While consider a typical ferromagnet, where we have a typical permanent magnet, where being up or being down, it depends on what you've done before, if you have magnetized in one direction or the other. So who will be I mean, why is not the system fluctuating up and down? It cannot fluctuate, but that would be the equilibrium state. Maybe if you wait ages, you will see this system being at equilibrium, because maybe every million years it will switch, and then this will be the equilibrium behavior. But we have not time to see it. So if we don't wait enough, we see systems that are not at equilibrium, and this is the typical case of ferromagnets. We see them standing there in a non-equilibrium minimum for a very long time, and ferromagnets are exactly that case. In that case, what we have to do, instead of calling thermodynamic potentials, we call it free energies. And then we impose much weaker conditions on them in order to understand, let's say, the energetics. For example, we have seen that the Gibbs potential is the free energy minus mu zero HAM. And here we assume that we consider as a thermodynamic system both the magnetic material and its magnetostatic field. And then what we can do, we can ask that the variation with respect to change of the magnetization of this Gibbs potential, and we use Gibbs potential because we control HA, is at least a minimum. We are in a minimum condition for the Gibbs potential. And then this is the condition that we can ask. So what's the aim of our future description of ferromagnets? To find the free energy, to describe the free energy of ferromagnets. Because then, if we are able to have a description in terms of the free energy, then we can write the Gibbs free energy in terms of Landau, minimize, so find where this energy, I prefer not call it potential, but call it energy, is minimum, and then this will be a possible state for a ferromagnet. If it is a state that will be realized, it will depend on a lot of things. For example, on previous history, if you magnetize in one direction, if you magnetize in the other direction, and so on and so on. So, in the next, we will discuss terms that could be there in a magnetic material, and then specifically in a ferromagnet. And we will see that we have quite complicated terms. So, but this at least is the context where we work when we work out a theory of a ferromagnet. So, where we have non-equilibrium Landau free energies. Okay, so this we have to say in order to complete, and what you can read. So for magnetic energy and Poynting theorem, you find in the book of Jackson, again in the book of Bertotti. The part of magnetostatic energy and magnetic work I've taken from the book of Giorgio Bertotti. Very, very well done. If you, let's say, for thermodynamics, I can suggest the book of Cullen, which is a very simple and basic, but very complete introduction to thermodynamics, and also contains, I think, the last edition apart on magnetic materials. Okay, I think we are in time. And I stop here.